All right, so the first thing that I want to talk about for today is instantaneous power in three-phase circuits. So let's say, just for the sake of argument, that I have a Y connected load. That has some characteristic impedance, resistance, and inductance. Like so. Here's A, B, and C. And let's call the voltage drop across the A phase VA of T, the voltage drop across the B phase of the load B of T, and the voltage drop across the C phase of the load VC of T. And the current through the A phase, IA of T, the current through the B phase, IB of T, and the current flowing through the C phase, IC of T. So VA of T will be of the form Vm cosine omega t plus some arbitrary phase angle theta v. Since this is a balance load, then we know that VB will be of the form Vm cosine omega t plus theta v minus 120 degrees. And VC will be of the form Vm cosine omega t plus theta v minus 240 degrees. Our currents can be expressed in a similar fashion. So we would have Im cosine omega t plus theta I for our A phase. Im cosine omega t plus theta I minus 120 degrees for our B phase. And Im cosine omega t plus theta I minus 240 degrees for our C phase. So everybody catching what I'm throwing thus far? We just have three voltages all 120 degrees out of phase with each other, three currents all 120 degrees out of phase with each other. And because we're dealing with instantaneous power, we're looking at time varying voltages and currents. So the instantaneous power absorbed by our load is going to be the combination of the instantaneous power absorbed by the A phase of our load plus the instantaneous power absorbed by the B phase of our load plus the instantaneous power absorbed by the C phase of our load. So the instantaneous power absorbed by the A phase is simply going to be VA times IA. The instantaneous power absorbed by the B phase is going to be VB times IB. The instantaneous power absorbed by the C phase will be VC times IC. And now I'm going to use that exact same trig identity that I've used multiple times in this class to multiply all those guys together, right? So that's going to look like 1/2 Vm Im cosine theta V minus theta I plus 1/2 Vm Im cosine twice omega t plus theta V plus theta I. I'm just going to make a note here. This is our A phase contribution. Now let's look at our B phase contribution. So I'm going to have a 1/2 Vm Im. And what I'm doing right now is I am taking this angle right here as a single angle and subtracting from it this guy right here. So omega t minus omega t is going to look like 0. Negative 120 degrees minus negative 120 degrees is also going to look like 0. So I'm just going to get a theta v minus theta I yet again. Now I come to the AC part where I'm just going to add those angles together. And that's going to look like twice omega t plus theta v plus theta I minus 240 degrees. So this is our B phase contribution. And lastly, I'm going to have our C phase contribution. Which, following the same rules as we did for the B phase, is going to look something like this. So my instantaneous power is just the sum of all of these things added together. Now I want us to look here at the AC portion, okay? So I have 1/2 Vm Im cosine twice omega t plus theta v plus theta I plus 0 degrees for my A phase term. And then I have 1/2 Vm Im cosine twice omega t plus theta v plus theta I minus 240 degrees for my B phase term. And 1/2 Vm Im cosine twice omega t plus theta v plus theta I minus 480 degrees for my C phase term. Well, negative 480 degrees is the exact same thing as negative 120 degrees. So what happens when I multiply three things together that have equal magnitudes but are exactly 120 degrees out of phase with each other? So if I were to just take one angle 0 plus one angle negative 120 plus one angle negative 240, what do I get? I've asked you guys to do this before. 0. So all three of these AC terms exactly cancel each other out. So we wind up being left with 3 times the DC term, or 3/2 Vm Im cosine theta v minus theta I. What's interesting about that? So this is an instantaneous power. Do we see any dependence on time whatsoever? No. The instantaneous power absorbed by a balanced three-phase network is actually a constant. So the instantaneous power and the average power are literally the exact same quantity. Okay? This is one of the principal advantages of a three-phase system, particularly when you're powering rotating electric machinery like induction motors, synchronous motors, etc. Because they are delivered a constant amount of power, they develop a constant amount of torque. And so we don't see any vibrations or anything like that. No spurious energy loss, really. Okay. All right, so our instantaneous power relationship, fairly straightforward. Effectively, it's just 3/2 times the instantaneous power in a single phase circuit, or the average power in a single phase circuit. Now let's look at complex power. So I'm going to draw a whole circuit out here because we're going to infer some things from it. So I'm going to start with a YY system. Like so. Let me label my terminals. So A, capital A, B, capital B, C, capital C. Label my voltages where appropriate. And now label my currents. Sorry, that should be B. While I'm at it, I'm actually going to label some line voltages and some line currents as well. Because this is getting busy enough, I'm not going to explicitly draw the voltage VCA, but we all know that it lies between the C transmission line terminal and the A transmission line terminal. Okay, so if I wanted the complex power that is absorbed in the A phase of the load, how would I determine that? What's my equation for complex power? V times I conjugate. So VAN times IAN conjugate, which I could express as the magnitude of VAN times the magnitude of IAN with an angle of theta VAN minus theta IAN, which is the same as the magnitude of VAN times the magnitude of IAN times the angle of my Y-connected impedance. Perfect. Are we okay with that? Anything seem suspicious or incorrect? So, since nobody's piping up, I'll assume you're all okay with it. So, what about my B phase? I should be able to get very similar results. So I could say that this would look like the magnitude of VBN times the magnitude of IBN with an angle of theta ZY. And similarly, for my C phase, this is going to look like the magnitude of VCN times the magnitude of ICN with an angle of theta zy. Now, what do we know about the magnitude of the B phase voltage, how it compares to the A phase voltage? The same thing. And the C phase voltage is the same as the B phase voltage, which is the same as the A phase voltage. What about the magnitude of those currents? They're also all the same, which means the complex power absorbed in the A phase, excuse me, the B phase of the load is literally identical to the complex power absorbed in the A phase. Complex power absorbed by the C phase is also identical, so that the total power, which I'll just call here SY, is equal to SA plus SB plus SC, which is 3 times the magnitude of our A phase voltage, the magnitude of our A phase current, with an angle of theta zy. I'm running out of room here, so I'll just tuck this in below. I'm just going to choose to write that as 3 VP, where this VP just represents the phase voltage, and I'm going to put RMS here, times IP RMS with an angle of theta zy. Where, like, once again, VP RMS is just the magnitude of that phase voltage expressed as an RMS voltage, and IP RMS is a magnitude of that phase current expressed as an RMS current. All right, so what if we wanted to put things in terms of our line voltages and line currents? Right? So what's the relationship between our phase voltages, excuse me, our phase currents and our line currents for this YY system? They're the same thing. IAA must be identical to IAN because they're flowing through two impedances that are connected in series, right? So if I take this SY, let me write it over here, I could now say that 3 VP RMS times IP RMS with an angle of theta zy, that has to be equal to 3 VP RMS times IL RMS with an angle of zy, where that IL RMS is just the magnitude of my line current. Okay. Now, what's the relationship between my phase voltages and my line voltages for a Y-connected system like this? Square root of 3 angle 30, right? So if I only wanted the magnitude part, it's just square root of 3. So 3 VP RMS is actually going to look like square root of 3 VL RMS, because there's another factor of square root of 3 already buried in there. And let me explain that in a second. Where this guy right here is understood to be root 3 VP RMS. Because we know that there's a square root of 3 difference between the phase voltage and the line voltage magnitudes in our Y-connected system. Okay, so we now have this equation for our total complex power absorbed by our Y-connected load, and this equation for our total complex power absorbed by our Y-connected load. What if we had a delta connected load? What do you think would happen? Disagree. Literally identical, right? So when we have a Y-connected load, we know that our line currents and our phase currents are equal to each other. And our line voltages and our phase voltages are related to each other by √3 angle 30 degrees. We beat that to death, right? Way back when we were looking at the differences between delta connections and Y connections, we observed that the phase voltage in a delta connected system and the line voltage in a delta connected system are literally the exact same thing. Let's look at something here really quickly. So let's say that I have a delta connected impedance. Doesn't matter how my source is connected. Doesn't matter whether or not my transmission line has any impedance. So that's why I'm just representing that by the ellipses on the left-hand side. See delta, draw the delta, there we go. So my phase currents would be IAB, IBC, and ICA respectively. If this were the A, B, and C phase terminals, well, my line currents would be these currents right here. IAA, IBB, and ICC. So we can actually figure out what the relationship is between our line currents in this delta connected load and our phase currents in this delta connected load are by just applying Kirchhoff's current law, right? So I can see pretty easily that my line current, IAA, is just IAB minus ICA, which is nothing more than IAB times 1 minus 1 angle negative 240 degrees. Can anybody remind me what that is? Because we used that last class meeting. Yep. So we can see that the magnitude of our line currents and the magnitude of our phase currents in a delta connected load share that √3 relationship in their magnitude, much like the voltages did for phase voltage and line voltage in a Y-connected system. So effectively, one set of quantities is always going to be the same, and the other set of quantities, magnitudes, are always going to be related by √3. So realistically, we can just get rid of this Y and use the exact same expressions regardless of whether we have a delta connected load or a Y connected load. So those are our relationships for our complex power. Okay. Now we can break things down and look at our average power, right? So let me write things out here. So S in general, can be expressed in terms of our phase quantities as 3 VP IP angle theta z. And in terms of our line quantities, this looks like √3 VL IL angle theta z. Our average power is nothing more than the real part of our complex power. So the real part of 3 VP IP angle theta z is just 3 VP IP cosine theta z. And we can do something similar over here with our line quantities. So we just need the real part of our complex power. Which is going to be √3 VL IL angle theta z. Our reactive power, Q, is just the imaginary part. Isaiah, how may I help you? Oh, yes, thank you for that. So our reactive power is the imaginary part of 3 VP IP angle theta z, which is just 3 VP IP sine theta z. And here we'd have the imaginary part of √3 VL IL angle theta z, which just comes out to be √3 VL IL sine theta z. And lastly, our power factor is just the ratio of our three-phase average power divided by our three-phase apparent power, which is just the cosine of the angle of our impedance. So effectively, we have identical relationships to what we had for single-phase circuits, except that we multiply them by 3 because there are 3 phases. I know it's groundbreaking stuff. Yes. All right, so let me do it down here. So I'm going to start with S 3-phase is equal to 3 times VP RMS times IP RMS with an angle of theta z. Okay, we understand where that part came from, right? Now I'm going to say, since IP RMS is equal to IL RMS for a Y connection, and VL RMS is equal to root 3 VP RMS for a Y connection. This guy right here could be expressed as the square root of 3 times the square root of 3 VP RMS IP RMS with an angle of theta Z. This root 3 VP RMS is just VL RMS, and IP RMS is just IL RMS. Square root of 3 times square root of 3 is 3. Am I mistaken on that? I feel pretty strongly that root 3 times root 3 is 3. Yeah, I'm not trying to be a dick. It's just this one right here. I'm literally just saying 3 is equal to the square root of 3 times the square root of 3. Right. Yeah. And then it would work the exact same way also because, so since VL RMS is equal to VP RMS for delta, and IL RMS is equal to root 3 IP RMS for delta, we could just associate this root 3 with this guy over here for a delta connected, and we wind up with the exact same relationship. Okay. Yep, no problem. All right. So I'm trying to decide if I want to work a numerical example problem or if I want to just jump ahead to three-phase power factor correction, and then we can look at example problems for the remainder of the class. I'm looking at the three-phase power factor correction, just because that's the last material that we have. So after we finish that up, everything is just working examples to help you guys understand what's going on. Okay. So three-phase power factor correction. So we all have I'm assuming here, and I hope I am assuming correctly, that we all have a basic understanding of how single phase power factor correction is supposed to work, because you've now been exposed to it in at least 2 classes in the curriculum thus far. Okay. So over here on the left-hand side, I am just going to put a balanced three-phase source. Here's my A terminal, B terminal, and C terminal. And then over here on the right-hand side, making sure to give myself plenty of room, I'm going to put a balanced three-phase load. Here is the A phase, B phase, and C phase terminal of said load. And now I'm going to connect these guys together with transmission lines where I'm not going to bother about any impedance for right now. Okay. So I want to make something very clear here. I'm looking at my balanced three-phase source and my balanced three-phase load as black box networks, meaning that I do not know, nor do I remotely care whether they are delta connected or they are Y connected. They're just going to be connected to each other through transmission lines because that's how we connect them. Doesn't matter if the source is delta or Y, doesn't matter if the load is delta or Y. Okay. Now let's say that I needed to correct the power factor of my source because it was operating at too low of a power factor. For a single phase circuit, we simply place a capacitor across the terminals of our voltage source. That's all we're going to do in three-phase power factor correction as well, except that we're not going to use one capacitor, we're going to use three capacitors because we're going to correct all three phases. So instead of just a single capacitor, we install a capacitor bank. We have two different options. We could install a Y-connected capacitor bank, or we could install a delta-connected capacitor bank. Okay. So I'll put the Y-connected capacitor bank in red. It would look something like this. Okay. So here's my connection to my A phase. I'm going to jump over my B phase, jump over my C phase. Here is my capacitance CY. This guy down here effectively represents the neutral point. Here's my B phase. An identical capacitor CY. Here's my C phase, a third identical capacitor CY. I do not physically need a neutral conductor on either my source or my load to install this capacitor bank. I'm just wiring the bottom leg of all of those capacitors together at a common point, giving me a Y connection, okay? So it literally doesn't matter if my source or my load is in Y or delta, I can always do this. Alternatively, and I'll do this in blue, I can install a delta connected capacitor bank. So that would look something like this. I would have a capacitance C delta connected between the A and B phases, an identical capacitance C delta connected between the B and C phases, and a third capacitance C delta connected between the A and B phases, or excuse me, the A and C phases. Once again, does not remotely matter whether my load is connected in delta or Y, whether my source is connected in delta or Y. Either of these options are available, okay? So effectively, this is going to follow practically the exact same rules as single phase power factor correction. The thing that we have to pay attention to is to make sure that we're only looking at the average power per phase, and we need to make sure that we're using the correct voltage drop across our capacitor, depending on if we have a delta connected bank or a Y connected bank, right? So just to revisit things here, for single phase power factor correction, our equation for C was P old times the tangent of theta old minus the tangent of theta new divided by omega times the magnitude of the voltage drop across the capacitor squared. We're going to use the exact same equation. We just need to make sure that this is the power absorbed by a single phase, and this voltage could be VP RMS or VL RMS, depending on whether our device or our capacitor bank is connected in a Y connection or a delta connection. Okay, so we just need to pay attention to what voltage the capacitor is going to see, which depends on how we're going to line that connection. So let's look at an example, and this is going to force us to revisit our power relationships in. Okay. So let's say that a balanced three-phase source feeds a balanced three-phase load. Actually, let me sneak this in here. 24 megavolt amperes, so a large industrial load. Operating at a power factor of 0.8 lagging. If the line voltages are 34.5 kilovolts RMS at 60 hertz, determine the value of C, a single capacitor in our capacitor bank, such that the source supplies power at a power factor of 0.94 leading. So I'm going to approach this very similar to how I approach these problems in circuits 1, and probably how I approach problems here in circuits 2 as well. I want to just figure out what pieces of information to apply in my equation that I already have. Okay, so what pieces of information do I have or can I get very easily based on current information? So omega is 2 pi f, so that would be 120 pi radians per second. Okay. I believe that I can get theta old and theta new very easily as well. So theta old should just be the inverse cosine of 0.8. Grab a calculator here. I think it's 36.87. Yep. Theta new will be negative the inverse cosine of 0.94. Putting the negative sign out front because we were specifically told that our power factor is leading after power factor correction. So that looks like negative 19.948 degrees. So what am I missing? I think this P old in my voltage. So P old is going to be the same regardless of whether my capacitor bank is connected in delta or Y. So how am I going to find that based on the information given? Power factor and and apparent power. Sure. Right. So P old should just be my apparent power times my power factor. So that's going to be 24 megavolt amperes times 0.8 comes out to be 19.2 megawatts. Anybody have any problem with that? Literally just from the definition of power factor. And so the last thing that I need is my voltage. And again, this depends on whether or not my capacitor bank is connected in delta or if it's connected in Y, right? So let's assume that we have a Y connected capacitor bank, right? So CY would be P old times the tangent of theta, excuse me, this should be theta old first, minus the tangent of theta new over omega, and then I'm given my line voltage squared. Do I need to do anything to that line voltage in order to take into account that I have a Y connection? Right, so how am I going to get there? Divide by root 3. So I'm dividing by root 3, and then I'm squaring it, and that's in the denominator of my denominator. So what's that going to look like? A 3 out front. So we have everything to plug in, so we could plug it in there. I'll just put equal, etc. What if we had a delta connected capacitor bank? It's literally just going to be CY over 3. So if we know one, we can immediately get the other one because we know how the square of the voltages are related to each other, right? So let's throw some numbers at this time, right? So 19.2 times 10 to the positive 6 times the tangent of what I have stored in my calculator as X minus the tangent of what I have stored in my calculator as Y divided by 120 pi times 34,500. Oops, I meant to square that. That seemed aggressively large. This is way better. Give me 47. Ooh, what the hell just happened? Sorry. 47.622 microfarads. Divide that by 3, and I get 15.874 microfarads. So I'm surprised no one has asked this yet, but what are the advantages and disadvantages of using a Y-connected capacitor bank versus a delta-connected capacitor bank for power factor correction, right? So we can see pretty obviously that the delta-connected capacitor bank is always going to use or result in a smaller capacitor value, right? So why wouldn't we always just use a delta connected capacitor bank? Because a smaller capacitor should arguably be a cheaper capacitor. It's all about the fact that the delta connected capacitor, while it uses a smaller capacitor, it sees a larger voltage because it sees a line to line voltage, which will always be larger than the phase to neutral voltage, right? So effectively, it might use a smaller capacitor, but it has to be rated for a higher voltage, and that could potentially make it cost more. So realistically, you're always just going to look at both to see which one you can get for cheaper, and then that's what you're going to install. It's all about saving people money. All right, so we've covered all the material that I intended to cover for this class. Yes, sir. For a three-phase, yes. You might hear a star configuration. That's just a Y configuration. I don't know why they call it star. Usually, I think a star specifically has a neutral conductor as well. But a star is just a fancy Y. Yep. So Y and delta is the only different ways that we can rearrange these. So, it has been taxing for sure. Just because of the All right. So if I am trying to solve for those voltages, VAB, VBC, and VCA, those line voltages, I would have found VAN first and then multiplied that by √3 angle 30 degrees. I think that's what I would have done. Line currents and line voltages. Okay, so line currents are easy, line voltages. So let's see, what did I do here? I found IAB and then I used Ohm's law. 88.210. Let me see something here. No. So just for sake of argument, solving it in a slightly different way. So our single phase equivalent circuit, I don't like that color. 120 angle 60 volt RMS. This was 0.8 plus J 1.4. Twelve plus J 15 is going to look like 4 plus J 5. Divide both of those things by 3. Four plus 5 pi, 4.8 plus 6.4 J. $94.047, angle 58.210. VAB is just VAN times √3 angle 30 degrees. Is 166.358. Angle positive 88.210 degrees. Which is exactly what I got. For sure. Uh-huh. So 88.210 minus 120 is negative 31.79. right, I guess, yeah. Uh, so, let me double check some things here. 19.2 times 10 to the 6. So that's from the megawatts. And then I have, let me actually, so in my calculator stored as X, I have 36.869897 blah, blah, blah. Stored as Y, I have negative 19.948 blah, 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 so that can be lazy. So 19.2 times 10 to the positive 6 tangent of X minus tangent of Y. That's probably what it is. 120 pi, and then 34,500 squared. Yeah, so this guy should come down here. I forgot the 3. You're absolutely right. So 47.622 microfarad, multiply that guy by 3, 142.866. Thank you for that, Landon. You're correct. Ian. Correct. That's for one of the capacitors in the capacitor bank. You cannot, I want to be clear about this. I don't think anybody actually thinks it can be done, but one of the most common mistakes that I see the students make for this stuff is that they forget to just look at the, I did it. I forgot to change this. My original answers were actually correct, but it was completely by accident. So let me go back to that son of a bitch. So I was about to be like, one of the mistakes that I see you guys make the most is this, and then I just realized that I definitely made that mistake. So the mistake that I made is that I should have divided this by 3, because I want the P old for a single phase, not for all 3 phases. So that would change this to 6 point something, 19.2 over 6. Excuse me, 19.2 over 3 is 6.4 megawatts. Which should yield this answer and then the answer that we had originally. So I forgot to divide by a factor of 3, but then I also happened to forget to multiply by that same factor of 3 and stumbled my way into the correct answer completely on accident. But what exactly are we? Okay, so let's clear things up, right? When we looked up at our equation here, I said P old, but that we needed to pay specific attention to the fact that we need to use a single phase old average power. The 24 MVA is for the 3-phase source, which means each phase is absorbing 8 MVA. 8 MVA times our power factor would give us 6.4 megawatts of average power. And that's the number that should have been used. Sure. You can divide by 3 at the beginning or divide by 3 at the end. It doesn't matter. It's just dividing by 3. That's how math works. Yeah. I will, I believe I usually say specifically on the problem, the total apparent power or something like that, so that you always know whether or not I'm giving you things on a per phase basis or for the 3-phase system, so that there's no ambiguity there. Yeah, for sure. One page, front and back, standard 8.5 by 11. Don't be a dick about it. No legal sheets, all that kind of stuff, just like the last exam. Yes. I'm trying to remember if it's 2 or 3 circuits. Yeah, just 3-phase. I don't remember off the top of my head whether it is 2 or 3 circuits, but it's no more than 3 circuits. And then each circuit will have multiple smaller questions kind of leading you through things. So the questions that I might ask you are extraordinarily similar to your homework questions. Looking for line voltages, line currents, phase voltages, phase currents, average power, reactive power, apparent power, complex power, size of the capacitor in a delta connected bank, size of the capacitor in a Y connected bank. That's about all I can ask you. I have no idea. Sure, probably. The reason I have no idea is because I don't remember how many 36s I own, if it's 3 or 4. I know that there is a TI 36 at home on my home office desk. I only have one in my bag. Okay. I already have multiple extras, but sure. Yes. Absolutely. Yeah, it is optional. So if you, let me be clear about that. Friday, if you feel comfortable with everything and you're working on your homeworks and all of it makes sense, you do not need to show up on Friday. We're not going to cover any new material whatsoever. If you need assistance with anything or anything just isn't making sense, come ask questions. Absolutely.
So, this is the correct circuit for number 5. Yeah.
Sure.
So is this just this part of it?
So the current in the A phase of load 1, so yeah. So if load 1 is the 4 plus J4, then that's the current that's just flowing through the 4 plus J4. Yes.
So then I'm very confused. How do I use, because I can't do current division because I don't know any of these values.
What are you trying to find?
I here to here. Yeah, so I guess.
Okay, so the phase current's in the delta connected source. Okay, so that's easy enough. You have the current, you have the impedance, so you can find the voltage. If you know the voltage drop, that means you can find the current flowing through this guy. Add those two currents together, and that's your line current, and then KCL at the other side. Yep.